Welcome back for the fall semester. Welcome to the IQUIS seminar series. It's my pleasure to introduce Waseem Bakr from Princeton. So Waseem did his PhD at Harvard with Marcus Greiner, where they basically invented quantum gas microscopy, first for bosonic atoms, which really kind of opened a new field for cold atom physics. He then went to MIT, where he worked with Martin Zwaarlein, and among the things that he did there, he kind of helped invent quantum gas microscopy for fermionic atoms, which has really been exciting in the past several years. And now as a professor at Princeton, he's continued that research with fermionic atoms and also kind of invented quantum gas microscopes for molecules, which is really cool. Waseem has won many awards, including the DAMOP Thesis Prize, the Sloan and the Packard, and the AFOSR Young Investigator Program. So I'm very happy to have Waseem here, and please join me in welcoming him.
Great. Thank you very much, Jake. Is mic working fine? Yeah? Okay. So yeah, it's a pleasure to be visiting again here at Illinois. It's been a while since my last visit. Yes, I'm going to be telling you about work we're doing at Princeton, studying many-body physics with ultracold gases of atoms and molecules. So let me start first with a big picture for the work we do in my group. We are interested in studying strongly correlated systems inspired by materials that people study in condensed matter physics. So these are materials like these high DC superconductors or quantum magnets or moire materials where you have these interacting systems of electrons or spins that give rise to emergent phenomena, which are very interesting, some of which have technological applications. We are interested in understanding these systems on a microscopic level. But of course, that's very hard to do on a classical computer because you have to solve the quantum many-body problem. It's hard to do simulations for more than a few dozen particles. And so the idea here is this idea of quantum simulation that goes back to Richard Feynman. He suggested a long time ago that instead of doing the simulations on a classical computer, it makes much more sense to do the simulations on a quantum system. So ideally, what you want to have is a synthetic quantum system, which is highly programmable and very easy to control, and use that to do your simulations of the basic Hamiltonians that describe these systems. And people are pursuing this approach with different synthetic platforms like ions or superconducting qubits. Today, I'm going to be telling you about how we do this with ultracold gases. So the systems we're working with are very dilute vapors of atoms or molecules. Typically, the atoms I'll show you here are like alkali atoms. You put them in a vacuum chamber. The typical spacings between the particles and the gas are on the order of a micron or so. And to study quantum physics with these gases, you have to cool them down to very low temperatures in the nanokelvin regime. We have ways to get there with laser cooling and evaporative cooling. And once you cool them, they become quantum gases. They behave much like, say, if you have a gas of fermions, like the Fermi gas in a metal. Or you can have bosons, and then you'd have a Bose-Einstein condensate. And then to make them look even more so like a condensed matter system, we can load them into optical potentials that give them a band structure. So those are known as optical lattices. So we take laser beams and interfere them with each other. They produce periodic patterns of light, which the atoms experience as a periodic potential through the AC Stark effect. So you get a band structure. And so the analogy here is between the atoms moving in this periodic potential of the optical lattice and the electrons in a solid moving in the periodic potential of the ionic lattice. So you can think of this essentially as an enlarged model for condensed matter physics, where you've blown up the system by 4 orders of magnitude. The atoms are, of course, a lot heavier. The spacings here are microns rather than angstroms. So the energy scales are much lower. They're in this nanokelvin temperatures. The dynamics is very slow. It's milliseconds. So we think of this as a good thing because it's easy to measure dynamics in these systems. We have a very good understanding of the microscopic Hamiltonians that describe these systems. We can write them down with the precision of atomic physics, unlike the crude models typically used for condensed matter physics. And so we understand these systems a lot better. at least on the level of the Hamiltonian, we can write down, but still there's the emergent many-body physics to understand. We can control a lot of the parameters of the Hamiltonian often in real time. So for example, you can do things it's hard to imagine how you do them in a condensed matter setting. You can control, for example, the tunneling of the particles in the lattice in real time by just changing the laser intensity, the interactions, the geometry of the lattice, and so on. And finally, as Jake pointed out, we have this technique of quantum gas microscopy that allows us to go and probe these systems with visible or near infrared light down at the single particle and the single site level. So in a way, maybe reminiscent of things like you can do with scanning tunneling microscopy, but even more powerful, as I'll show you shortly. So here's the kind of picture you get with a quantum gas microscope. So this is a gas of lithium-6 atoms, which I use in my lab. So lithium-6 has 3 protons, 3 electrons, 3 neutrons, so a total of 9 fundamental particles, making it a fermion. This gas of fermions is two-dimensional. So we have a two-dimensional lattice here, and the atoms are moving around in it. We start by producing a degenerate Fermi gas, a very simple state which we understand very well. And then we can ramp on an optical lattice to quench the kinetic energy of the system, enhance the effect of the interactions, and get into a strongly correlated state. So basically, we can go into a state where there's complex correlations and entanglement in the system. The particles are delocalized, they have interactions between them, and then we can go and project this many-body wave function onto a particular realization in the density and spin. We can go and measure on every site, each green dot here is a single atom. We can see each single atom. So the analogy here in the solid state would be seeing every single electron in your system simultaneously. And you can do this over and over, prepare the same system in an identical way, prepare it again and again, and repeat the measurement, and extract any sort of correlation function you want. It doesn't have to be a 2-point, it could be 3-point, 4-point, 5-point, okay? Any endpoint spin and density correlation function you're interested in. So you can characterize the many-body wave function in a way that's not possible in condensed matter physics. And this is a technique that has, as Jake said, we started with it back in 2009 at Harvard, for bosons and then for fermions. And now it's spread out and being used by many groups around the world. Okay, so what sort of physics can you study with this? Well, the paradigmatic Hamiltonian you can look at when you have fermions on a lattice that are strongly interacting is something called the Fermi-Hubbard model. This is a Hamiltonian that was proposed way back by Phil Anderson shortly after the discovery of high-TC superconductors as a basic Hamiltonian which you can use to study maybe the essential physics going on in these systems. So the Hamiltonian here has 2 pieces. There's a kinetic energy piece where you have tunneling of fermions between sites, neighboring sites. So you create a fermion, you destroy a fermion on one site J, and you create another one on a neighboring site I. And here's sigma is the spin index. So we have in these experiments 2 spin states in analogy to the spin states of the electron. And those are encoded in 2 hyperfine states of the atoms, acting as a pseudospin. We're preparing usually single band models. We lower the temperature so that the fermions are in the lowest band. And then the fermions can interact by landing on the same site, and they have a strong on-site interaction U. Okay, so this type of Hamiltonian is deceptively simple. People have been working on it for now like over 4 decades. We still don't know what the low temperature phases are. You can study it on various lattice geometries. A lot of the early work in atomic systems was focused on the square lattice. Now people are branching out to other sorts of lattice geometries. In the square lattice, the inspiration was the cuprates. And so we're interested in how much of the phenomenology of the cuprates can we reproduce with this type of Hamiltonian. So let me start first by just quickly reviewing some of the work that has been done with square lattices. I can't show you a phase diagram for the Hubbard model because we don't know it, but what I can show you here is the phase diagram of the cuprates measured experimentally. This is a highly stripped down phase diagram which shows some of the key phases that appear in the phase diagram as a function of temperature and doping. So here by doping, what I mean is you call a system undoped if you have an equal number of fermions and sites in the lattice on the average. If you add some particles, it's particle doped. If you remove some, it's hole doped. And we can start here in this regime of where it's undoped, or we can call it also half filling. There in the cuprates, you have these strong interactions where this ratio of U to T is large, and those suppress density fluctuations, and you end up with one atom per site. This is a state known as a Mott insulator. And then if you lower the temperature of the system, then spin interactions kick in. There are no direct interactions between fermions on different sites, because you saw in the Hamiltonian, the interactions are purely on site. But you can have these virtual processes where an atom hops over to a neighboring site and hops back, and you create an effective spin-spin interaction through this super exchange. And that leads to antiferromagnetic ordering at lower temperatures. So these two phases, the Mott insulator and the antiferromagnet, are phases we understand very well from theoretical simulations of the Hubbard model. We know they're there in the cuprates. We know they're there in the simulations. And so they're good benchmark phases to test our quantum simulators on. Now, if you start to dope the system, that's where all the interesting physics happens in the cuprates. And there you have things like the famous D-wave superconductor here. And then there's, in the normal regime, there are anomalous behaviors and transport and spectral properties, which we don't understand very well. We would love to understand them. The theory gets very hard. The benchmark technique people use is something called quantum Monte Carlo, or the gold standard technique is quantum Monte Carlo. And there you kind of run, as you go to lower and lower temperatures, into something called the Fermi unsigned problem, which makes it impossible to understand these systems at low temperatures. And that's what we're hoping to do with this microscopy. Early on, people were able to see these Mott insulators, where you can take pictures of the system and see that as you crank up the interactions, you have one atom per site most of the time. There's some, if you're at finite tunneling, you have some virtual processes where, say, a particle hops over to a neighboring site and hops back. There are these antiferromagnets. So as I said, you have the super exchange, which leads to basically an effective model near half filling, which is a Heisenberg model. And so you get a Heisenberg antiferromagnet, where it's really a quantum antiferromagnet. So if you go and look at the pictures, depends on how you measure, like when you go and measure on a particular basis, sometimes the spins might not be aligned in your measurement basis and you don't see much correlations. Other times you'll see it. So you have to kind of repeat the measurement over and over again. And you can take an expectation value of the spin correlation function. So this is here a map of the 2-point spin correlation function measured this way. And you can see that there's indeed a checkerboard order in the spin correlation function indicative of an antiferromagnet. Okay, so those are the phases we understand very well. In fact, we can compare them to quantum Monte Carlo, and that's the way we do thermometry in these systems. Yeah. Yeah. Yeah.
Like one green dot, but then some of them are seemingly denser than one green dot. So are they doubly occupied?
No, so that's simple microscopy. There might be a little fluctuations in the illumination intensity, but there's usually, when you look at these pictures, there's just two peaks in one at 0 atoms and one at 1 atom. You don't see 2 atoms. The reason for that has to do with something called light-assisted collisions. So if you have 2 atoms on a site and you shine photons on them, very quickly they disappear from your system. They form molecules, or they just kind of disappear very quickly. And you're left with 0 atoms after the first few photons. And then the next 1,000 photons or so, you don't collect any light anymore. So the readout is very digital. You either read 0 or 1, but I'll show you ways later where you kind of can fix this problem. There are some which are brighter. They probably kind of, there's just a cluster of many sites close to each other, which have 1 atom per site. You can see here, because the diffraction limit of these microscopes is very comparable to the lattice spacing, which is also set by the wavelength of light, we can barely resolve these atoms, but you know the underlying square lattice structure. And so you can overlay a grid, and with a computer algorithm, you can tell with over like 99% fidelity whether you have an atom on a site or not. Okay, but the readout is digital. It's either 0 or 1. Okay. So the next interesting thing you could, I was saying something about thermometry. So you can compare this stuff all to quantum Monte Carlo, and you can leave yourself with one free fit parameter, which is the temperature, and that allows you to compare to fit a temperature to these systems using the correlations. And the lowest temperatures people have now reached are on the order of 15% of the tunneling. Okay. Okay, so another thing you could look at is now we start to dope the system. That's the more interesting regime. And a lot of the interesting physics there has to do with the interplay of charge and spin. So you have this background antiferromagnet, which can form the system, and then you can dope it a little bit. And you can see how, say, a hole moves around in a background antiferromagnet. And you can do this, you can do bulk measurements, you can do microscopic measurements. So these are some things we've done in my group, for example, where we studied transport close to the critical doping of the cuprates, where people see at high temperatures in the normal phase something called a strange metal. So there it's characterized by linear resistivity with temperature. And we discovered that indeed the Hubbard model also has something like a strange metal where you can see a linear resistivity with temperature. Here are more microscopic measurements of similar physics where you can, say, inject a hole into an antiferromagnet and see how it moves around and disturbs the antiferromagnet. And people see things like these magnetic Polarons where there's a local disturbance of the spin correlations around a dopant. Here, this is a more dynamical picture where you can see how the hole moves around in the antiferromagnet, but leaves behind the spin-on. And so you form this sort of object called the geometric string, which binds the two things together. These are things people had talked about in textbooks for a long time, but had never seen visually like this with a microscopy. Yeah. Yeah, so it's a whole other talk, but we don't obviously can connect leads and so on. But what we can do is, like in this experiment, we patterned the potential of the lattice so that we have a charge density wave of long wavelength. And we can watch the dynamics of how this out of equilibrium state decays. From that, we can back out diffusion. And from the diffusion, we can connect it through the Nernst-Einstein relationship to resistivity. Okay. Okay, so now I want to, any other questions? This was kind of review just to kind of set up the problem. Yeah?
What is a temperature range that this simulator can?
It's kind of at this point like about entering like kind of in the high part of the pseudo gap phase if it exists in the Hubbard model. No, the superconducting would be, so I told you the lowest temperatures are about 0.15 T, and the superconducting, if it's there, is probably going to be like 0.05, 0.03, although a lot of people are now talking about it's more likely to be a charge density wave. But I mean, this is all like subtle competitions between different things that are happening in the cuprates, but you can in the Hubbard model, but you can try to start like adding extra terms and try to favor superconductivity. Okay, so one of the nice things people have achieved in the last few years is now they've moved away from a lot of the early work was in square lattices. That's partially because when you set up a microscope, you kind of set up the whole system around a particular lattice geometry. But more recently, people have learned how to create lattices which are a bit more programmable. So I won't go into the technical details, but let me just say here that we have setups. This is, for example, in my lab, we have a setup where we can, with the same setup, just tune knobs and software and go between different lattice geometries. So we can, in the same setup, access things like square lattices, triangular lattices, honeycomb lattices, Kagome, Lieb, a whole kind of set of interesting condensed matter lattices by just tuning things in software. So I'm going to focus for the next few slides on physics we're doing with triangular lattices. So the underlying geometry is still a square lattice, but what we're able to do is to control the connectivity of the square lattice. So in particular, we can, so in the square lattice, we have this tunneling T between the neighboring sites. And what we can do is we can introduce this diagonal tunneling here, T prime, which we can control at will. So we can take the ratio of T prime, so we can set T prime to T at will. And so we can go from a square geometry when T prime is 0 to a triangular geometry when T prime is equal to T. We can crank up T prime larger, and then it becomes like 1D chains. And so the triangular lattice, of course, this has been studied for a long time. This is even earlier work, probably by Phil Anderson, where he was studying the Heisenberg model on the triangular lattice. And the interesting physics in the triangular lattice is, of course, the frustration. So if you have, for example, antiferromagnetically coupled spins on a triangular lattice, here's a plaquette. You can see if you put a spin that's up, pointing up here and pointing down here, they're happy, but the third spin can't decide what it wants to do. So this is this phenomenon of spin frustration. And that can lead to some very interesting and exotic phases in these systems. As a matter of fact, one of the early predictions of Phil was he was looking for the ground state of the system, and he suggested that it might be something like this, where you form singlets on each bond. So you pair up these up and down in a singlet, and then you overlay singlets everywhere in the lattice on all the bonds, but there's no reason to favor any particular configuration. So you form a superposition of all the different configurations. And this is this idea of a resonating valence bond state, which eventually led to spin liquids and so on. Turns out this idea was very inspirational and started the field of spin liquids, but was actually incorrect. And in the Heisenberg model that Phil was looking at, the actual ground state for the triangular Heisenberg model is a state where you arrange the spins in 120 degrees ordering in the plane. There is a way to solve the frustration by arranging them that way in this 120-degree Néel order. Okay, so this is just to show you that even at half filling, the triangular lattice is very interesting, even without doping. The square lattice, we understand things well, but in the triangular lattice, it's so much more complicated. So this is at half filling, a cartoon phase diagram of some of the phases you might expect as you vary this ratio of T prime to T. So remember, when T prime is 0, you're in the square lattice regime. If you crank up T prime to equal to T, here's the triangular lattice. And you can see already, for example, as a function of the interactions, in the square lattice, at any interaction, you have a Néel state. But in the triangular lattice, you go through a whole bunch of interesting phases. When you go to very large U over T, there's this spiral antiferromagnet that I showed you earlier for the Heisenberg model, because the Hubbard model becomes the Heisenberg model at half filling in the limit of very large interactions. But if you're at intermediate interactions, people don't understand things very well. So there's a proposals that this might be here, some sort of spin liquid that breaks time reversal symmetry. So this is some of the reasons people got very interested recently in looking at triangular Hubbard systems. And this is all without doping. If you dope, things get even more interesting and richer. Okay, so let me show you some of the work we've been doing more recently on this triangular Hubbard model. First, at half filling. So we can, again, look at spin correlations in the half-fill system. And this time, thank you for asking that question about the light-assisted collisions. I told you you can only get this digital readout, but in the Hubbard model on a site, there are 4 possibilities in a single band model. You can have a hole, an upspin, a downspin, or a double one where you have an up and a down on the site. So you'd like to actually kind of to have readout of all these 4 possibilities to get the full information. And so in our lab, we have an additional thing we do before imaging where we actually have a Stern-Gerlach step where we start with this single 2D system, but we can apply a magnetic field just before imaging to do a Stern-Gerlach separation into 2 separate layers, a layer which has the upspins and a layer which has the downspins. And then we can image both of them simultaneously on a camera. So we can get full readout now without this issue of light-assisted collisions. We can get the full readout of all the possible states, and we can fully reconstruct the snapshot of the Hubbard model and then construct any endpoint correlation function. So here in particular, we're looking at the 2-point correlation function. So this is actual data here, where the color is encoding the spin-spin correlation function that we measure. So blue means that the spins are anti-aligned, and red is they're aligned. So for example, if you fix the central spin here, those spins around it are primarily anti-aligned. And then the ones further out here are aligned with the spin in the spin-spin correlation measurement. Yes?
When you do your Stern-Gerlach and separate your 2 layers, are you separating them in the transverse image plane? Is your field of view large enough that you don't really?
No, it's in the vertical. Yeah, so basically we have two sets, we split up the image and we have two sets of lenses that are focused on the different layers. Yeah. Okay, so of course, this is again a quantum antiferromagnet. There's a lot of fluctuations. You have to take the expectation values. But here I've overlaid the classical 120-degree nail order that you would expect with these arrows. So this is just a suggested cartoon to orient you. And you can see, for example, if you fix the spin here and look at this spin, they are primarily anti-aligned with each other in this 120-degree order, right? They're almost anti-aligned, and that's why you measure a blue correlation. And then if you measure this one here, they're primarily aligned. Yeah.
You don't like the vector and the so I get this, the blue and red is the experimental results.
Yes.
But like directions are like unknown.
That's right. You would have to kind of, you can measure in different bases, but yeah, I mean, extracting this pattern, the chiral order is harder. But yeah, I mean, we just kind of like choose, for example, let's look at the SZ basis and measure SZ correlation function, the connected correlation function, or you can rotate it and look at SX, SX. Of course, here in the Hubbard model, it's all SE2 spin symmetric, so you don't get more information. But if you can try to do local rotations, then maybe you can do what you're thinking about, like trying to map out this actual order. Okay. All right, so this is all connected to the spin frustration. And now I'd like to switch to a different phenomenon, which might be less familiar, which is something called kinetic frustration. And this was actually inspired by very recent work that's just happened last year in the Moiré community. So probably some of the condensed matter people here might be working on these Moiré systems. This is work from the Shan and Kinfai Max group at Cornell and Imamoglu's group at ETH, where they were studying these bilayer systems of transition metal dichalcogenides that they twist relative to each other. And when you twist these things relative to each other, these layers, you get this Moiré lattice, which is triangular, and it's reasonably well described by a triangular Hubbard model. So the effective description is what we're studying in our quantum simulator. And what they're able to do in these experiments is they can control the doping with a gate. They can electron dope, they can hole dope. And what they observe in the experiments is that if they electron dope the system and measure the spin susceptibility, they see ferromagnetic behavior. If they hole dope it, they see antiferromagnetic behavior. So this is magnetism that's controlled by the doping. So that was very interesting work coming from these experiments. And our theory collaborator, Eugene, and his student, Ivan, were trying to build a microscopic model of what's going on. And they had a picture which they suggested to us to go and test with our quantum simulator. So here, this is all bulk measurements. So now I want to show you how we can go and study the microscopics of what's going on with these triangular Hubbard systems. And the key part of the story is this kinetic frustration, which I want to explain over the next couple of slides. So you've seen spin frustration, but this triangular lattice supports this different kind of frustration. So to understand that, let me start first by just imagining a triangular lattice where we put a single fermion in the lattice. Very simple, single fermion, so single particle physics, and very simple Hamiltonian where you can just have this fermion tunnel around. Okay, so we can, of course, diagonalize this and get a band structure. And here's the band structure of the triangular lattice. Unlike the square lattice, it has particle-hole asymmetry. And you can minimize the energy by putting this fermion at zero quasi-momentum. And then it lowers its energy by the number of nearest neighbors, which is 6 times the tunneling matrix element. Okay, so let me go through this again in a more contrived way. So I can ask, okay, so I want to lower the energy of this particle, so I want to delocalize it. I can delocalize it, say, on this bond. And for the proper sign of the tunneling, it wants to form a symmetric superposition of being on this site and this site. Okay, so there you go. Here's a symmetric superposition. But then you can also delocalize it here and delocalize it here. And then you delocalize it everywhere, right? And this works out. You have the same phases everywhere. And so you create this zero quasi-momentum state, okay, where it's a superposition of all the possible sites. Okay, so now let's repeat this, but in a different setting where instead of a single particle, we're going to put a single hole. So now I'm going to imagine a spin polarized system where all the spins are pointing up, and I'm going to punch out just a single hole. And we're going to ask, what is the ground state in this case? And what you would, it's still, there's no interactions because we only have one spin state in the Hubbard Hamiltonian. But now it's more natural to write this Hamiltonian in terms of hole operators rather than particle operators. So you want to say, create a hole by destroying a fermion. So H dagger gets replaced, the C gets replaced by H dagger. Let's do that in this Hamiltonian. So now you have H dagger. And you have to remember, for these are fermions, so you want to normal order the operators. You don't want them to appear in this order. You anti-commute them, and that flips the sign. Okay, so now the sign has flipped in the Hamiltonian, which means that when you want to go and repeat the same thing I did earlier on a bond to delocalize this hole, now instead of forming a symmetric orbital, you want to form an anti-symmetric spatial orbital. That's the one with the lower energy. Okay? We can repeat this on the neighboring bond, works out, but then you can't do it for the third bond of the plaquette, right? This is an unhappy bond here because if you delocalize, you have the same phases. You can't form an anti-symmetric orbital. So this is a phenomenon of frustration, but it's frustration in the spatial degree of freedom, not in the spin degree of freedom. Okay, that's why we call it a kinetic frustration. And in the band structure, all you have to do is you flip the sign of the tunneling, so you flip the band structure. And what you want to do now is to put the holes, their ground state would be here. At what used to be the maxima would now be the minima, right? So they're sitting at a finite quasi-momentum. So what you find is because of the particle hole asymmetry, where what used to be lowered by 6T is now lowered by 3T. So the hole isn't able to delocalize as much as the particle. It's not as happy as a particle. And so we say that the hole is frustrated. Another way to think about this is that when you think about this hole's motion in the spin polarized background, it can move on different pathways in the lattice, which will destructively interfere and reduce the mobility of the hole in the system. Okay? Okay, so how do we make the hole happy again? How do we resolve the frustration? Well, you want to remove the indistinguishability, which leads to this destructive interference. And you can do that by flipping some spins around the hole. That way, when the hole moves around, if it moves in this path where, say, there's this flipped spin versus this path, there's some which way information. Okay, so that's what we're going to do. We're going to flip some spins around the hole to unfrustrate it. Okay, so the simplest way to think about this is on a plaquette. We're going to just consider a single plaquette where we crank up the interactions to infinity. So you have, let's say we put two particles in the plaquette so that we have a single hole. So now it's a hole doped system with two particles. And we can solve the problem in two sectors, the triplet sector and the singlet sector. So here's the triplet sector. So we have two particles in a triplet with one hole. And the only thing that the hole can do in this problem is move around this plaquette. And here you go, it's moving around. And at the end, it swaps the two spins. But they're in a triplet, so nothing interesting happens. So you swap two spins in a triplet, still the same state, right? So boring. Let's repeat this now with the singlet sector. Now when you go around, you flip the two spins in a singlet, you get a minus sign. And this minus sign is exactly the minus sign that was required to kind of solve the problem we encountered earlier. So it unfrustrates the system. Okay, so flipping a spin around a hole makes it happy. And how much happier? What is the sort of the characteristic energy scale for this object to bind the hole to the spin flip? Well, the only thing that I have in the problem is here the tunneling. So the characteristic energy scale is the tunneling. Okay, so you have a system where you're binding to a hole a spin flip, and you're forming this composite object, which we might call a polaron. So this polaron consists of anti-aligned spins in vicinity of a dopant. And the binding object energy of this object is on the order of the tunneling energy scale. Okay. So that's kind of pretty amazing, right? You have antiferromagnetism appearing on the system, and its energy scale is not the super exchange, which is the usual thing, which is usually a small number when the interactions are strong, but some much higher energy scale, which is the tunneling. Okay. So this is essentially leading to high temperature magnetism. Okay, so how do we see this in the experiment? So this is now experimental data. What we have to now measure is not a 2-point correlation function, but a 3-point correlation function. Okay, so what we do is we prepare our Hubbard system with ups and downs in it, and we're going to dope it away from the multi-insulator. So in this case, we hole dope it. The first thing you do is you go and find a hole in the picture. Okay, and then you go and evaluate the 2-point correlation functions around the hole. So that's why it's a 3-point. You first find the hole, and then you evaluate the spin correlations around the hole. And what you find is in the vicinity of, so you look at this connected 3-point correlation function where you're asking, how does the dopant disturb the background magnetism? And the result we see is that around the hole dopant, we observe, as we reduce the doping more and more, we observe the formation of this magnetic polaron where around the hole dopant, there are antiferromagnetic bonds forming right around the hole dopant. So that's the blue color. And further out, they turn to red. So it turns out, actually, the full story is that if you crank up the interactions to infinity, then there's no more super exchange in the problem, right? So it looks pretty boring, but when you dope, these dopants mediate an effective magnetism in the system, which looks a lot like the super exchange magnetism. So you get something like an antiferromagnetic Heisenberg model, even in the absence of super exchange. This is just coming purely from the tunneling. And the resulting magnetism has a temperature scale of T. So you start to form this spiral antiferromagnet whose characteristic energy scale is T. So in the pictures, the key thing here is that the hole is clustering with these antiferromagnetic bonds. Interestingly, if you look for particle dopants instead of hole dopants, so these are doublons now, you find that around a doublon, you form ferromagnetic bonds. So it's the opposite story. This is this particle hole asymmetry part of the triangular lattice. We said earlier with the hole, we had to deal with this frustration. Here with the doublons, they're particles, so that we don't have to do this whole story with the anti-commuting hole operators. So here they actually prefer to have ferromagnetic interactions. Yeah. You again measure, so you're measuring basically a 3-point correlation function. You're evaluating the expectation value of on 3 sites. First, you find on this particular site, do I have a doublon, for example? And then if it has a doublon, what is the spin here and the spin here? So we first separate. So basically, the end result of the separation with the Stern-Gerlach is we can reconstruct from the snapshot the entire population, whether it's up, down, hole, or doublon. And then we can do this over and over by repeating the system over and over in the same way and repeating the measurements like 100, 200 times. And then we can extract the expectation value of the connected correlator. Okay. And so here around the doublon, we find ferromagnetism. And as we dope less and less with these particle dopants, we find that there's basically a ferromagnet forming everywhere. And this is basically, for the theorists here, it might be reminiscent of something called Nagaoka magnetism. So this is a very seminal sort of work by Nagaoka in the Hubbard model. A long time ago, he suggested that a single dopant in the Hubbard model can lead to ferromagnetism everywhere. And this was theorized for a long time. It was never observed in a real material. And the reason is that the conditions for Nagaoka's mathematical theorem are very stringent. You have to have a single dopant and very strong interactions, essentially infinite interactions. Here with the triangular lattice, it turns out things are much more forgiving. You can go to finite doping, finite interactions, and you see this Nagaoka magnetism. Okay. So I just want to maybe wrap up this part of my talk with telling you why I think this is super exciting. It's not only that you have this high temperature magnetism, but there's also recent theoretical work that's proposing that this might be a route to high temperature superconductivity. Because the polarons we're seeing here are the simplest sort of polarons you can have, where you have basically a single hole or a single dopant binding to a single spin flip. But you can have more complex objects where you have multiple spin flips and multiple holes binding together. So those are described in this paper here. And so that might be a way where this polaron, you can have 2 holes binding to each other. And when the holes bind, they can condense and form a superconductor. And the energy scale is still T. Okay, the prefactor is smaller, but the energy scale is still T, not the super exchange. So this might be a way to high TC superconductivity. Okay. So maybe in the last 10 minutes, I'm going to just now switch gears to something different. So this is more along the lines of what Jake was doing as a PhD student. So this is polar molecules. So I told you about how with these Hubbard models we've discussed so far, all you have is on-site interactions. But in condensed matter physics, long-range interactions can lead to a lot of interesting stuff, right? And we've been missing that in the cold atom community for a long time. So there are many ways people have been discussing how to get long-range interactions. You can get magnetic interactions with certain types of atoms. You can get stronger electric dipole interactions with things like molecules. So that's why we're interested more recently in developing microscopy for molecules. And so the molecules are, of course, more complex. So you have now, the simplest case is to have, imagine two atoms bound together in a molecule. And let's say it's a polar molecule. So they tend to be bialkali molecules. So here in my lab, we have sodium rubidium. So these bialkali molecules now have much more degrees of freedom. Not only can they translate around like an atom, but they can rotate, they can vibrate, right? And all these degrees of freedom you can store quantum information in. But they also have these long-range interactions, these polar interactions, which can lead to significant interactions even when they're in different sites. Okay, so the coherence between these various internal states like rotational can be very long. They can be on the second scale, so they're good for storing quantum information. And if you're thinking of, for example, quantum computing, these interactions would be a way to do gates. Okay, so, but I'm more interested in the quantum simulation aspect of this to study condensed matter systems. And there's two things you can do with these molecules. One thing is to just let them roam around in the lattice and interact with each other. And then you would get Hubbard models, but now with long-range dipolar interactions. Another thing you can do is you can pin them down on sites, and you can encode a qubit in two rotational levels. So a spin 1/2 in two rotational levels. So you can imagine, for example, a molecule that is not rotating as one level of the qubit, and a molecule that's rotating with 1 unit of angular momentum. And these tend to be pretty long-lived, like on the second scale. And now they can interact with each other through the dipolar interactions. So these can be used to engineer things like spin systems. Okay, so the challenge with working with molecules is that they're hard to cool. So with atoms, we have these powerful techniques like laser cooling, where you exert radiation pressure on the atoms to slow them down and get them cold. But with molecules, if you try to cycle on a particular transition and scatter many photons to slow them down, it doesn't work because you have all these different levels. As soon as you scatter a few photons, you fall into a different vibrational or rotational level, and that's the end of the story. Your laser is no longer resonant. So people spent a while learning how to make cold molecules. For example, one way is they've identified certain classes of molecules which can be laser cooled. It's very special classes of molecules. They have cycling transitions or near cycling transitions. Another approach that was pioneered at Gila, where Jake was is to say, okay, well, I'm going to give up on cooling the molecules, but maybe what I can do is I can cool two gases of atoms all the way to degeneracy, and then pick atoms from each of these two gases and bind them together into a molecule in situ and form an ultra-cold molecular gas. And that's very successful. People have formed now degenerate Fermi gases and Bose-Einstein condensates of molecules that way. Okay, so in our recent work, we've combined aspects of both of these approaches in the sense that we now have these we have these ultra-cold gases, which we can probe with microscopes at the single site level. So what I'm going to show you is basically pictures where we can tell in the lattice where each molecule is and what its internal state is. And so we can do microscopy on these many-body systems of molecules. Okay, so the standard, so the approach we use in my lab is something along the lines of what Gila did. We can produce these degenerate gases of atoms, in our case, sodium and rubidium BECs. We can bind them into molecules through something known as a Feshbach resonance, where you form basically the least bound state of the intermolecular potential, interatomic potential. And then we can put them all the way in the ground state using a 2-photon transition. So now they're in the absolute row vibrational ground state where they're not rotating and they're not vibrating. And this state is very nice because there they have a large dipole moment, so they can interact with each other at long range. Okay, so the experiment proceeds as follows. We start with a random sprinkling of atoms of rubidium and sodium in the lattice. On occasion, a rubidium and a sodium atom will be on the same site. If this is the case, then we can convert them with perfect efficiency, 100% efficiency on a site to Feshbach molecules. We can blow away the remaining atoms, and then we have a pure sample of a random sprinkling of molecules in the lattice. And we can verify their molecules by measuring their binding energy. So if they're Feshbach molecules, they have a very weak binding energy on the level of 10 megahertz or so, but then we can put them all the way in the ground state with this 2-photon transition, and then they have essentially like hundreds of terahertz of binding energy. Okay, so how do we image them? I told you these molecules don't have these cycling transitions. So what we do instead is we actually just reverse the entire process. We break them apart back into atoms, and then we image, say, the rubidium atoms, and the rubidium atoms act as tags that tell us where the molecules are in the lattice. Okay. So one important aspect of this Feshbach preparation is that the molecules, like I said, are prepared in a very well-defined quantum state. They're in a single hyperfine, rotational, vibrational, electronic state. All the quantum numbers are well-defined. So they're indistinguishable molecules. And we can now encode, as I said, spin 1/2 in rotational states, and we can use this microscopy not only to read out the positions of the molecules this way, but we can also read out their state. So we can reverse the Stirap process that puts them in the ground state and read out whether they're, say, in the lowest state or the excited state, rotational state. Okay, so let me just, yeah. So one of the early experiments that was done I think by Jake and his team in June's group was indeed encoding these spin 1/2 in these molecules and then watching them interact and showing that there are indeed these long-range interactions. And the way the molecules interact is, let's imagine you have a molecule that's in the lowest rotational level, so it's not rotating, and you have another molecule that's rotating with 1 unit of angular momentum, okay? So what these can do is they can exchange their rotational excitations with each other, okay, through this dipolar interaction. And so what you realize is naturally a quantum spin exchange model with a dipolar coefficient. And the experiment that was done in this work was basically to prepare the molecules in a superposition. So let's start with all the molecules, say, pointing down in the lowest state, but you can prepare a superposition where they're pointing along the X state. Okay, so all of them are now in X, and you're asking what is going to happen under this XY model. So if you have a quantum XY model, you don't have the ground state when you're pointing along X. So what you get is basically out of equilibrium dynamics. And the system starts to, if you look at the contrast in the system, it will decay. And that is indeed what was studied in this experiment. Now, the difference in our experiment is we can go and measure the correlations in the system and watch how this out of equilibrium dynamics leads to a spreading of correlations and entanglement in the system. So let me, maybe in the last couple of minutes, just quickly flash by some of these results. So here I can show you first that we can isolate 2 rotational levels. So the splittings here are on the gigahertz level, very similar to superconducting qubits. We can isolate 2 rotational levels and drive Rabi oscillations between them. So you have a nice 2-level system. We can measure the coherence time of this 2-level system, and it turns out to be on the hundreds of milliseconds time scale. So this corresponds to hundreds of interaction times over which the system is coherent. So we can really study this quantum magnetism over hundreds of interaction times. And here are pictures looking at how these correlations spread in the system after we do this out of equilibrium quench. Okay, so we can really, for these molecular systems, now observe how the correlations spread using the same microscopy techniques I described earlier for atoms. Okay, so let me, I think I'm running out of time here, so I'll skip all of this. Sorry about that. Okay, so to summarize, we've really, like, at this point, pushed molecules to the point where we can do quantum simulations with them. We have good control over the internal states. We have long coherence times. We can observe the interactions between them. And now we can do these experiments where we can measure with these microscopes the molecules at individual sites. All right, so thank you very much for your attention.
All right, thanks, Waseem, for a great talk. Any other questions for Waseem? Yeah, go ahead.
States like and it's something that I think is sort of a how are we kind of narrowing down? Maybe I'm too far to your talk, but how are we
Yeah. So, I mean, obviously, it's not the same quantum state. It's not a, for the earlier part with the atoms, it's a thermal state. So we're preparing the same density matrix, if you wish. Yeah, but we can prepare the same density matrix over and over and measure the expectation values in there. For the molecules, indeed, there is like a classical disorder in the molecule positions, depending on which sites have happened to have a sodium and rubidium. So all the correlation functions we're measuring in that case are averaged over this order. Now, more recently in my group, what we're working towards is, I showed you pictures where people have realized now, for example, degenerate gases or BECs of molecules. So now you can imagine doing the exact same thing people do with atoms, which is to prepare Mott insulators of the molecules. And then you would start with a well-defined like state where you have one molecule per site. So that's what we're working towards.
Any other questions?
Please explain again how spin frustration is resolved in.
Spin frustration, I mean, in the Heisenberg model, the ground state people find is this 120-degree order. So you kind of put the spins in the plane and they orient themselves at this 120 degrees. In the case of the Hubbard model, if you go to finite interactions, this is no longer the case. There's at intermediate interactions, people see in the simulations some sort of non-magnetic insulator. And there's speculation that this might be some sort of spin liquid. So there it wouldn't be, yeah, it would be some sort of, there's no, the ground, it's a spin liquid ground state. There's no order parameter, or at least not a trivial order parameter.
Okay, let's stop here. We'll have lunch upstairs. You're welcome to join. And please join me in thanking Waseem again.